Section 11.3, we're going to talk about angles. And as we take a look at this, we're going to define some different types of relationships between or among angles, and that's where we're going to start. Our first description is that of vertical angles. Vertical angles are pairs of angles that appear across from each other whenever lines intersect. And in this diagram, there's two sets of vertical angles. I'll mark them with different colors. There's this set, right? They're across from each other. And let's go this color. There's this set. Vertical angles are congruent. I'm not going to prove that to you, but if you imagine this, it's a pretty easy thing to imagine, and here's why. Let's say, for instance, and I'm going to use numbers to give you an example, that this is 40. Does anybody know what the angle E that's marked at the top would be if the one I marked over here is 40? It would be 140. How do you know? Yeah, because they're along a line, right? This line. So they have to add up to 180. Now imagine this line right here. What would this purple angle on the right side have to be? 40. And this would work no matter what numbers I picked. And you could do that the same thing for the green angle at the bottom. Okay, so vertical angles are congruent. That was not a proof. That was a justification by example. That's what that was, okay? Another relationship between angles is complementary and or supplementary. Ones you've heard before, usually mentioned in the same breath. Complementary angles are two angles whose measures add up to 90 degrees. One of the ways we talk about these angles is we say that one of these angles is the complement of the other one. Supplementary angles are two angles whose measures add up to 180 degrees. I just used that fact a moment ago. We would say that one of these angles is the supplement of the other one. Now notice, both of them reference how many angles? 2. It's not 3, it's not however many you want, it's 2. So when you're looking and trying to describe whether the angles that you're talking about are supplementary or complementary, it always has to be 2 angles we're talking about. So for example, in this diagram over here, if I talked about angle AOC, that one that I just marked in, it's kind of green. So this is angle AOC. Then the complementary angle to that would be what? COF, or you could say FOC. Okay, those would be complementary angles. Now there's more than just that in that diagram, right? Yeah, we have several sets of complementary angles within that diagram. But we can't talk about, for example, oops, I would not be able to say that angle AOB and angle BOD and angle DOF are complementary because there was 3 of them. It's isolated to 2. The same thing's true about supplementary angles. So let me give you one angle in this diagram down here and you tell me the supplementary angle. Let's go with angle AOB. What angle is supplementary to angle AOB in my diagram? Angle BOD. Good. Another relationship that we can talk about that exists among pairs of angles are interior angles. So this is a diagram of parallel lines, okay? They don't necessarily have to be parallel for this to be the argument. It's usually how we think of it. But if you have 2 lines that they're intersected by a third line, both of them are intersected, that line that intersects them is called the transversal. So this T right here is the transversal in this diagram. Now, my page is going to switch, but you're still going to have the diagram, I think. Let's see. Yes, ma'am, I do. All right, so here's that same diagram. Interior angles are angles that lie between the pair of lines. So the lines that are referenced here are lines L and M. And there are there are interior angles. So name me an interior angle of this diagram. Angle 8 is an interior angle. What's another interior angle? Angle 3 and angle 2, and there's one more. Angle 7. Those are all called interior angles. And they're specific to this diagram, right? And where they're located and where those lines L and M are located. Angles when compared that are interior angles can be called alternate interior angles if they're on the opposite sides of the transversal. So you've just listed 4 interior angles. So let's just take the first one you listed, angle 8. So angle 8 is located right here. Okay? What is the one other angle that's an interior angle on the opposite side of the transversal? It would be angle 2. One of them is on the left-hand side of the transversal, the other one's on the right. So angle 8 and angle 2 would be called alternate interior angles. And in some situations, that means they're congruent. They're equal measure, but not all. So hold off on just saying alternate interior angles are congruent. There's some conditions that have to be true before that's true. Okay? But they do have the relationship. They're still called alternate interior angles, even if they're not equal. What about angle, what else do we have? 3. It would be alternate interior to angle 7. Okay, exterior angles is the next one. Exterior angles are angles that lie outside the pair of parallel lines, or I'm sorry, the pair of lines. They don't necessarily have to be parallel. What are your exterior angles in this diagram? 4, 1, 5, and 6. Those are my exterior angles. And we can talk about them just like we did alternate interior angles. We have alternate exterior angles. They're on the outside and they're opposite. So if I start with angle 4, what is the angle that is the alternate exterior angle to 4? It would be 6. It's on the other side of the transversal and on the outside of the 2 lines L and M. So angle 4 and angle 6. What's the other pair in this diagram? Angle 1 and angle 5. Very good. All right, our last comparison, I think, is corresponding angles. Corresponding angles are angles that are in the same position where the transversal intersects one line as it is where it intersects the other line. So let me give you an example. Angle 4 corresponds to angle 7. Because if you sort of imagine this hitting right here, they're both in the top left corner of where the transversal hits the line. All right, so I'm going to write that one down. Angle 4 and angle 7. Is that what I had? Yeah. Angle 4 and angle 7. Give me another pair. Angle 8 and angle 5. Very good. What's another one? There's 4 sets, right? What else?
1 and 2.
Yep, angle 1 and angle 2. And then there's one more.
3 and 6.
Yep, 3 and 6. These are corresponding. And again, under certain conditions, these would be congruent pairs of angles. So we need to know those conditions before we say it. They don't have to be congruent, but under some conditions they are. So what's the deal? When would these actually be congruent? Well, what happens if they are congruent? What would happen to be the case? What happens if we have corresponding angles congruent? Well, if corresponding angles are congruent, then alternate interior angles are congruent, alternate exterior angles are congruent, and our lines are parallel. So here's the cool thing. Knowing any one of those 4 statements automatically gives you all 4 of them. So if you know your lines are parallel, you get all those congruencies. If you know one of those congruencies, you get all the rest of them, plus you know that the lines are parallel. Okay, just because the lines are not parallel, though, doesn't mean they don't have the relationship. The relationship simply isn't that they're congruent. Okay, so if parallel fails, none of those congruencies happen, but they're still called corresponding angles, alternate and exterior angles, the same way. So we're going to construct parallel lines using a triangle. This is on page 659, so if you just want to not write it down and reference it later in your book, that's fine. I'm going to talk through it and write some details down. But I want you to have an idea of how it works because it's interesting. So we're going to start with a line M. Kind of in the middle of what you have going on, some space on either side of it. So let M be a line. Well, let me see if I have space on another slide. I don't. I should put arrows if I'm going to call it a line. It will be detailed. Let M be a line, and point P not on M. Okay, so this is my line M. I'll label it. And P is a point not on M. We'll put P right here. All right, so we're going to create a triangle. I called it ABC in my notes, so we'll say ABC, where one side lies on M. That is one side of my triangle. We'll call it an edge even would be better. One edge lies on M. I'm going to draw it below because it'll make the picture a little easier to work with. Oh dear. There we go. All right, so I have a triangle. It's underneath my line M. It doesn't have to be, but it works well to draw it this way. And just so that I'm clear, I'm going to call this A, B, and C. Let me write down what I'm going to do, and then I'll actually show it to you on the board. We're going to lie a ruler alongside AC. We're going to slide triangle ABC along the ruler until AB, side AB, intersects P. This will create line L where L is parallel to M because corresponding angles, I will say, are congruent. Okay, so, whoops, we've written it all. I'm going to actually do it so that it makes sense now, okay? Okay, so imagine big ruler in here anymore, I guess. Okay, so imagine this is a ruler. It's not, it's actually a compass, but imagine for a moment it's a ruler. And we lie this ruler right here. And then we actually had a piece of paper that was the triangle itself. And we slid this triangle up until it hits line P. What's going to happen as I slide my triangle up is eventually my triangle is going to run into P alongside AB. So it's going to look something like that. Slid along there. It's not great, but you got the idea, right? Move it over so it should be lined up like that. That's better. So you actually see this line that we already created from before. That's where my ruler was. Okay? And you can imagine sliding the triangle from the lower spot where the triangle is to the upper spot where the triangle is. And I've got this line now that's been created up here through point P. That line is called L. That's what I've called it. And it is going to be parallel to the line M. And the reason it's going to be parallel is because this angle and this angle are congruent. How do I know they're congruent? They're created by the same triangle, right? It is the same triangle moved, so we would actually say it's a congruent triangle. But those angles are the same, and if the angles are the same, then the lines have to be parallel. So again, this isn't a proof that that statement earlier is true, but it is a visual argument of how you could create it using triangles. Okay? All right, I want to talk about another one that's kind of a fun fact. I actually am teaching another geometry class this semester. Dr. Marsh and I were speaking the other day, and we affectionately called it big kid geometry, not because you guys are little kids, but because we go into geometry in another dimension, which makes it a little bit different than you guys are talking about. But right now we're still doing all the same kind of Euclidean stuff, and we used this fact. Actually, I forgot this fact in the middle of class. Not forgot it, but I forgot to use it, and it would have made my life a lot easier. And when I realized it later, I actually recorded a YouTube video and I sent it to them and said, do it like this instead, way, way easier. The sum of the measure of the interior angles of a triangle is 180 degrees. You know that's fact, right? You know that to be true. So I would like for you to, you know what, I'm just going to tell you what it is, and then we're not going to do it today because I want to make sure that we get finished. Imagine you had a triangle on a sheet of paper that you cut apart all of the edges. So you broke it apart. And you broke it apart into 3 triangles. Okay, everybody good? And then you took these angles, A and B and C, and you attached each of these vertices at the same point in space. So you moved each of those points so that this angle down here is where you started. So this is A, B, and C. We'll call it P. And we put angle A on here, right here. We put it along this side, and it created this piece right here, and here's my cutoff piece. Oops, I made it cut off. Let me do that. Here's the cutoff piece. So this is actually angle A, and it's been repositioned. And then my other piece, my angle B, gets repositioned, and it ends up being right here. So here's angle B, repositioned. What do you suppose is going to happen when I attach angle C after this happens? I know I'm asking you to do it without really doing it, but what do you think? They're going to form a line. And it's a really good justification for why this actually works. It's just, you know, all well and dandy to tell a kid that they all add up to 180 degrees, but if you actually were to do this one, would we have had time, and you tear it apart, it's pretty cool that it works, that they all piece together and they actually add up to 180 degrees. So this, again, is not a proof, but it's a really good visual example where you can do it with hands. Kinesthetic learners, right? Y'all are going to have some of them, where you can justify why this really works. Not only does it work for triangles, you can do it very well for quadrilaterals as well. Does anybody remember what the sum of the angles are inside of a quadrilateral? Think of an easy quadrilateral. What's an easy quadrilateral? A square is an easy one to look at. A square has 4 90-degree angles, so what's the sum of that? 360. Yeah, it's 360. So you could do this same argument with a square. You tear it all into pieces and you line all up along the edges. It would be more convincing if you did it with just an arbitrary quadrilateral and did the same thing instead of specifically a square. And you can see that no matter what the quadrilateral looks like, when you piece it together in this way, it completes a full circle, okay? And a full circle has that 360 degrees. So what I'd like to do, though, is to tell you how that works in general and how you can figure out what happens when you then have like a pentagon or a hexagon. Because the only ones you can do the visual demonstration for with the torn up pieces of paper are the triangle and the quadrilateral. And the reason is because the angles get too big to be able to justify that way. The sum gets too large, okay? So let's take a look at what happens when we've got a picture over here of a quadrilateral. So this is an arbitrary quadrilateral. And what you see on your paper and see on my screen is that it's sort of been divided up into two other shapes. What has it been divided into? Two triangles, right? There are two triangles here, right along this line. And what is the angle measure inside of each triangle? 180. So if I were to add up all the angles of one triangle with all of the other angles of the other triangle, I'd get 180 plus 180, which would also then be 360. So that's a very nice justification of how we can use just the information about the triangles to talk about quadrilaterals. But it doesn't stop there. You can do that argument with any polygon. So the next shape is a what? It's a pentagon. I've got 5 sides. Now, what's important when you divide these up as we keep working is that you're dividing them up along the same vertex. Do you see how they're both split right here? They have to share a vertex in common for this to work. And it doesn't matter in this diagram. They're forced to do that here. But in a minute, in the next diagram, that's not forced. So if I took a look at this one and I added up those, how many triangles do you have? 180. So I can add 180 together 3 times, or I can do 3 times 180 to give me, grab a calculator if you need it. It is 540. Good job. Okay, let's do it for a pentagon. I'm sorry, a hexagon. We're going to do the pentagon. Do you notice on this one, again, it's all attached down here at this particular point? You wouldn't necessarily have to draw in diagonals that way in general for a pentagon. For a hexagon. You had to for a pentagon. But in order to make this work, to make it make sense, you've got to make it that way in order to get your 3 triangles. So here's my 4 triangles in this one. The last one had 3 triangles. So I've got 4 triangles at 180 degrees each. What does that give me? 720. So let's take a look at the relationship that happens. With a triangle, we had 1 triangle. With a quadrilateral, we had 2 triangles. With a pentagon, we had 3 triangles, and with a hexagon, we had 4 triangles. What's the relationship between the number of sides and the number of triangles? Triangle has 3 sides, 1 triangle. Quadrilateral has 4 sides, 2 triangles. Pentagon has 5 sides, 3 triangles. What's the relationship between the number of sides and the number of triangles? There are 2 fewer. You got it. So if we have n sides, then we're going to have n minus 2 triangles. Does that make sense? Hexagon had 6 sides, 4 triangles. Okay, so however many sides you have, it's just 2 less numbers of triangles. And then the sum of the interior angles of the polygon is the number of sides, that was the n minus 2, and what did we multiply it by? 180 degrees. So this is really nice because this means that I don't necessarily have to just add 180 together a number of times. I know how many I can multiply it by to get the sum of the actual angles for my shape. So let's do it for 37 sides. I don't know about you, but I don't want to draw it. There's no way that I could draw this well. No way. But I can still apply this information. I have 37 sides. So how many triangles do I have? 35. And what do I do with the 35? I multiply it by 180 degrees. And what do I get? 6,300 degrees. So that's fun. 6,300 degrees. I don't want to draw it, right? But we can do the algebra. We can plug in the numbers to find out the sum. All right, I've got a couple of, I've got one example next that's specifically context. This is the house that I tried to draw last time. This one is a home plate of a baseball, for a baseball field. It has 3 congruent right angles. Do you see them 3 marked? And then the other 2 angles are congruent as well. What is the measure of one of the other 2 congruent angles? So tell me what you know in this diagram. There's several things you might mention. So tell me something you see. You can make 3 triangles because this is a pentagon. So if I were to add up all these sides and I had 3 triangles at 180, what's the total angle measure I'm going to get? We already did this once. It's 540. So 540 degrees is the total angle sum. What else do you know? Look at the picture. What do you know about some of those angles? Somebody started to say something.
It wasn't going to be that. I was going to say there's a quadrilateral.
Okay, there, yeah, you could break it apart into a quadrilateral and a triangle. That would still end up giving you 540. 3 of the angles are 90 degrees. Like you actually know what their numerical value is, right? So whether you write an equation or whether you simply take off the 90 degrees 3 times, how many degrees are left that you have to work with? $270. 270 is what we have right here. Is it 270 left over as well? Okay, so 270 is left. How many more angles do I have to work with? 2. So how would I find out what those angles are? I would need to take the 270 and divide by 2. What would that give me? 135. So the answer to the question, remember the question was, what is the measure of one of the other 2 congruent angles, is 135. That's an obtuse angle. Does that visually make sense for what you're looking at? Sure does. Well done. All right, we're going to go backwards on this question. This question says, in a regular polygon, the measure of each interior angle is 162 degrees. How many sides does the polygon have? Now, we talked a little bit ago that if we take n minus 2 times 180, this is the total sum, right? That's what it is. If the shape were regular, we'd have all of the sides the same. We'd have all of the angles the same. So if we had n gone, we're just using n as an arbitrary number, okay? Has n sides. And we were to divide both sides by n, that would give us the angle measure if it's regular. So imagine that we did that with our quadrilateral, right? Our quadrilateral over here, I'm going to use an example, was 360 degrees. 360 degrees, and in a quadrilateral we have 4 sides, 4 angles. So what's 360 divided by 4? 90, right? We get 4 90-degree angles. That's what we would do. We would divide by the number of angles we have. Now, what we know on this problem is that the total sum divided by n is supposed to be what? 162. So this is 162. So we've got a little bit of algebra to do here. What would I need to do to solve this for n? Multiply by n first. So I have n minus 2 times 180 on the left. And on the right, I have 162n. Because I've multiplied by n on both sides, and those n's canceled. What can I do on the left-hand side of this? I can distribute 180 times n is 180n. minus, what's 180 times 2? 360. And then I've got 162n over here, right? Cool, now what? Okay, subtract the 180n. Okay, so I've got negative 360 on the left. What's 162n minus 180n? Negative 18n. Then what would I do? Right. Okay, so what is negative 360 divided by negative 18? 20. There are 20 sides in this regular polygon. All right, cool fact about exterior angles. We talked about exterior angles a couple class periods ago. They're the beta ones that are listed. They're blue ones there are our exterior angles. The sum of all those betas, those exterior angles, is always 360. Doesn't matter what the shape is. Quadrilateral, or if it had 20 sides like the last example. The sum of the exterior angles is always 360. So in this diagram, this is saying beta 1 plus beta 2, beta 3, beta 4 plus beta 5. Is equal to 360. Okay, all those betas is equal to 360. All right, we're going to do one more example, and then we'll be done for today. Number 4 says lines A and B are parallel, and we are supposed to find the angle X. There's more than one way to do the problem. I'm going to do it using the most recent information that we've been working with, and I'm going to do it like this. This section has been all about polygons, right? Different shapes, different sizes of polygons. What I'm going to do is I'm going to make this a polygon by putting in a perpendicular line right here. Okay? So on purpose, these are 90-degree angles, and I can do that. You can always put one in. And then I'll be able to use some of the facts that I know about this polygon. So what is this polygon? It's a pentagon. So either by flipping backwards or by calculating it, I need to know how many degrees are in a pentagon. So how do we do that? It's got 5 sides. So how many triangles does it have? 3 triangles. So I would take 3 times 180. So how many degrees total are there in a pentagon? 540 degrees. How can I find out what angle X is? Subtract. What do I need to subtract? Okay, I've got 2 90s that I created. What else do I have? A 135 that's given, and a 140 that's given. So if I take 540 and I subtract off all those pieces, what do I have left over? 85 is right. Well done. It's 85 degrees. Some people, let me just draw your attention to it. We don't have time for group work. We'll do that as homework, but let me draw your attention to another possibility of how you could do the problem. Some people like to draw in a perpendicular here. And in doing so, what have they created? 2 triangles. Do you see the 2 triangles, everybody? Okay. And you know that a triangle has 180 degrees. So the degree marks inside of here would be 180, and of course this one's 90. Okay? Can you find this one right here? You could. How could you find it? Subtract it from 180. So what's 180 minus 135? It would be 45. And if you do a little bit of addition within the triangle, that would also mean that this is 45. Now that alone will not give you X. You have to do it for the lower triangle as well. So you can piece all this together. Here's a 90-degree angle. This one would have to be 50. So what would the missing one be? 40, sorry, I wrote the wrong thing down. You're right. Thanks for fixing that for me. 40. So what would the missing one be? That's my 50. That's the one I wanted to write 50 on. 50. So how would I find x if I've got a 45 on the top and a 50 on the bottom? Yeah, I take those two values and subtract from 180. And as long as we do both of those problems right, the one we already did and this one, we'll still get 85. Okay, so it just depends on what you see. There's not always one exact right way to do a problem. Sometimes there's more than one way.